All right, today we are going to take the notes on section 10.4, which is dealing with inscribed angles inside of circles. If at any point during the notes you need to pause the video so you can take a little bit more time to write things down on your note sheet, please feel free to do so. So to get us started, we need to talk about just some vocab. The first thing we have is an inscribed angle. So an inscribed angle is going to be an angle that has a vertex on the outside edge of the circle, and then each of the sides of the angle is going to form a chord of that circle. So it's going to go from one side of the circle to the other. So this angle here that's marked is the inscribed angle. And then the arc that goes on the exterior edge of the circle from end to end of that inscribed angle is called the intercepted arc. So we have a theorem that we've actually seen before with these inscribed angles. We needed it at one point to solve for a missing angle measure, so I had shown you this. But basically what this says is that if we have an inscribed angle, so that angle that goes back to the outside edge of the circle, it's going to be half of the measure of the intercepted arc. So in this particular circle on the left, I have my central angle here that's 120 degrees. And remember that the arc measure was the same as that central angle. So this arc here is going to be 120 degrees. The intercepted arc, the inscribed angle that corresponds with that intercepted arc, so this angle back here, is going to be half of that arc measure of 120 degrees. So it'll be a 60-degree angle there. So in this circle over here on the right, just showing that relationship in general, you have that inscribed angle of x, and then the intercepted arc on the outside edge of the circle is going to be twice that amount. Another theorem that we have is that if you have inscribed angles that intercept the same arc, then those angles are going to be congruent. So in this case, this arc AB has a inscribed angle of angle ADB. So this angle here is corresponding to that arc AB. But then we also have a second inscribed angle, angle ACB this way. They have that same arc. Arc AB intercepts both of them. So that arc is going to be the same arc, which means that these angles are going to be congruent. So this arc here would be double that inscribed angle measure. So the measure of arc AB would be 104 degrees. So we've got inscribed polygons coming up next. An inscribed polygon is just any polygon that's inside of the circle and that all vertices are on the circle. So it is important you see over here that all 3 vertices of that triangle or all 4 vertices of this quadrilateral are touching that outside edge of the circle for it to be considered an inscribed polygon. The circle that goes with that inscribed polygon is called the circumscribed circle. So just to show you a picture of what that looks like, if I just draw kind of something that looks like that first example from the previous slide, where I have triangle ABC, and triangle ABC is inscribed inside of that circle. If I call this point in the middle here X, for example, I could say that circle X is the inscribed circle. Circumscribed circle. Triangle ABC is the inscribed polygon, or in this case, inscribed triangle. So if you have a right triangle that is inscribed in a circle, so remember this means that all three vertices lie on the circle, then the hypotenuse of that triangle is a diameter of the circle. So here we have, if angle B down here at the bottom is a right angle, then that tells me AC is a diameter of the circle. And it's an if and only if, so it works in the opposite direction as well. If I have a diameter and I go put a triangle in, then that would be a 90-degree angle. Keep in mind that your diameter is equal to 2 times the radius. So if you know the radius, you can find the diameter or vice versa. If you have a quadrilateral inscribed in a circle, so specifically a 4-sided figure, the opposite angles are supplementary. Remember, that means they sum to 180 degrees. So we can use that to find all of these missing angles. The first one that I can find fairly easily is angle Z, because I know that 93 degrees and Z degrees are going to go together. They're supplementary. They add to 180. So I can say 93 degrees plus Z equals 180 degrees, and then subtract the 93. And then I'll get angle Z is equal to 87 degrees. So then I can put that 87 in. But other than that, I can't really do a whole lot with just this theorem to find angles X and Y because I don't know either one of them. But what I can do is I can look at this angle here that's inscribed in the circle. That's going to correspond to this arc here. And I can add together the 58 and the 106 degrees. That's going to be a total of 164 degrees for that arc. Angle X is going to be half of that arc measure. So X degrees is going to be 1/2 of the 164, which means that X is going to be equal to 82 degrees. Now that I've got the 82 degrees, I can find Y because I know that X and Y are supplementary. So I can say 82 plus Y equals 180, and then subtract the 82 to get angle Y, which is 98 degrees. And then finally, for this last example here, I'm assuming that all of the angles are congruent, so I want to find the measure of angle A. What we can do here is look at how many arcs we have across the circle, because each of these arcs here, like arc AB, is going to correspond to this angle ADB back this way. And that angle would be the same as each of these. So if all of those angles are the same, then all of our arcs would be the same. So if I just count up my arcs, I've got 1, 2, 3, 4, 5 congruent arcs. And the sum of those arcs, is 360 degrees. I can divide that by the 5 arcs that we have, and that will tell me that each arc has a 72-degree measure. So if I know that this is 72 degrees for the arc, my angle is half of that arc that's 72. So that tells me each angle is going to be 36 degrees.